this video, we're going to cover electromagnetic induction. So far, we've seen that an electric current will create a magnetic field. We also know that magnetic fields exert forces on moving charges. But if a magnetic field can push on a moving charge, can they also generate a current from nothing? This is the question that Michael Faraday also asked, so we will look at some experiments as he did. First, we'll connect a circuit to a piece of iron. When the circuit is closed, current will flow and generate a magnetic field at the center of the coil. We want to see if the magnetic field propagates through the iron to a loop connected to the other side of the iron core. And this circuit on the right is connected to an ammeter to measure if any current is produced by this magnetic field. What we find is that when the circuit is closed, the current needle is deflected, but only for a moment. Then, opening the circuit, the needle is again deflected and returns, but now it went in the opposite direction. We can do a similar experiment with a magnet in a single circuit. By moving a bar magnet near a coil of wire, we notice the ammeter reads a current while the magnet is moving closer to the loop, but then it stops when the magnet stops. The current needle then deflects in the opposite direction as the bar magnet moves away in the opposite direction. Changing the orientation of the bar magnet and repeating the experiment leads to the same result, but in the opposite direction. So we've seen that somehow changing the magnetic field through this loop causes a current. And we call this current produced by a changing magnetic field an induced current. Now let's look at a conductor moving in a magnetic field. This conductor has free charges that are free to move, and since they are moving perpendicular to this field, they will feel a force upward by the right-hand rule. This will lead to positive charge building up on the top of our conductor, leaving the bottom negatively charged. This also means that an electric field will form and point downward, away from the positive and toward the negative charge. As charge builds up, this field will grow stronger and exert a downward force on positive charges. This will continue until the two forces are equal to each other and thus cancel each other out. This will depend on how fast the conductor is moving and the magnetic field strength. Since there is an electric field, this also means there must be a potential difference over the length of the conductor. We call this potential difference a motional EMF, since it is the result of the conductor moving in a magnetic field. Now let's take our rod and allow it to slide across a U-shaped conductive loop that is fixed. If we again move this rod to the right in a magnetic field, we will generate an EMF, and this potential difference will cause current to flow around the conductive loop in a counterclockwise direction. This current will produce a magnetic field that is out of the screen, and we'll call this the induced field since it is produced by the induced current. We don't want to confuse this induced field with the external field that was already there. Now, if we look at our rod, while current is flowing upward, there will be a magnetic force on the rod to the left by the right-hand rule. This means if we want to move the rod to the right at a constant speed, these forces will need to cancel, and we can see what this force will need to be in that case. Now, in order to quantify the effect of changing magnetic fields to produce a current, we want to look at magnetic flux. Like electric flux, magnetic flux is the amount of magnetic field passing through some area or closed loop. We measure magnetic flux in units of Webers, and 1 Weber is equal to 1 Tesla meter squared. We can see magnetic flux can change in a few ways, the same as electric flux. It will depend on the angle the loop makes with the field, decreasing to 0 when the loop is parallel to the field, and maximum when the loop lies perpendicular to the field. The flux will also change if the area of the loop itself changes. Now we can look at a loop placed in a non-uniform field. If we look at a small patch of the loop, we can find the flux in this small piece of area. Then, to find the total flux in the entire loop, we can integrate over the entire area of the loop. Now, with the concept of flux in mind, let's look back at our experiments. We saw a rod moving in a magnetic field produced a current in this loop. We also saw that moving a magnet toward or away from a loop creates a current. And in both of these cases, the magnetic flux through the loop is changing. And we get the direction of this induced current by what's known as Lenz's Law. A change in flux induces a current, and the direction of this current will be such that it induces a magnetic field which opposes the change in magnetic flux. This change in flux can occur in 3 ways. First, the field can increase or decrease. Second, the size of the loop may change. And finally, the loop orientation relative to the field or vice versa may be changing. Let's take the example of field strength changing. For a field that is initially going downward through our loop, if the field strength decreases, the change in flux is upward, so the magnetic field induced will oppose this change and point downward. This means the induced current will move clockwise from a top-down view. If instead the field strength were to increase downward, the change in flux would be downward, and the induced field would oppose this change and be upward, and this will lead to a current that is counterclockwise. For a field going upward and decreasing, the change in flux is downward. This leads to an induced field upward and again a counterclockwise current. And finally, a field that is upward and increasing leads to a loop whose flux is increasing upward, so the induced field is downward and the current is clockwise. In all of these cases, we have an induced current when the magnetic flux is changing. But a current must be caused by an EMF, or a potential difference, and this leads us to Faraday's law. Faraday's law states that an EMF is induced around a closed loop if the magnetic flux through this loop changes, and it is equal to the rate at which this magnetic flux changes. If we have N coils or N loops, we just multiply this EMF by N. The direction of this EMF will still be given by Lenz's law. Let's look at a current loop in a changing magnetic field. This changing field will induce an EMF and thus a current that flows around the loop. And this means there's an electric field that moves around this circle. But what if we remove this current loop? If the field is changing, we find this electric field is still there. So now let's look at some relationships. We know the change in potential can be found by integrating the electric field in some direction, since the electric field points in the direction of decreasing potential. We just saw that an EMF, or potential difference, is caused by a changing magnetic flux. This means we can combine these to rewrite Faraday's law. We won't go into detail now, but notice this relationship connects the electric field and magnetic field. We will look at just how closely they are connected in the next video. But first, let's look at some applications of Faraday's law and this induced EMF. We've already seen an electric motor, where electrical energy causes a current, and then this causes a rotational motion of a conductive loop in an external field. So basically, we take electrical energy and turn it into mechanical energy. We can instead go the other way. Placing a conductive loop in an external field and rotating it, we can generate an EMF and thus a current in the loop. We can also connect the ends of the loops to slip rings such that every half turn, each end of the loop will connect to the opposite terminal. This allows us to control whether or not the voltage is alternating between positive and negative, or always staying positive. We call this an electric generator, since we are generating electricity by mechanically rotating the loop. We can quantify this EMF created by noting the area of the loop, the strength of the field, and how fast the loop is rotating in this field. Our other example consists of an iron core connected to two different circuits. The first, on the left, will be the primary circuit, which will be connected to an alternating voltage source, kind of like the one we generated in the last example. This alternating source will cause a magnetic field to change in the iron core, and thus change the flux through the secondary coil on the right. This coil will be connected to a load with some resistance, and the voltage across this load will depend on the relative number of loops between the two coils. We call this a transformer because the voltage on one side will be transformed, meaning it increases or decreases on the other side, and this voltage difference can be accurately controlled by the number of loops. So that's it for electromagnetic induction. Next time, we'll look more at the relationship between electric and magnetic fields and how they're more similar than we have noticed so far. So with that, I'll see you in the next video.